Okay, so in the last lesson, we looked at the different symmetry element to identify the point groups. Now we're going to follow the flow chart of the point group to identify the point group of a given molecule. To identify or to assign the point group of molecule, this is a yes or no flow chart we can use. The first question is to ask whether a molecule is linear or not. If it is linear, such in the case of diatomic molecules or carbon dioxide, then we ask the question whether that molecule has an inversion center. If the molecule does have an inversion center, as in the case of dinitrogen, we would classify this molecule as a d infinity H molecule. If the molecule does not have an inversion center, such in the case of CO, we would classify the molecule as C infinity V. If the molecule we are working on is not linear, we must then determine whether the molecule has two or more rotational axes that have threefold or higher. Or three folds, or you can say higher rotations. This question will determine whether the point group will classify the molecule as a highly symmetrical molecule. Example can be methane, hexachlorophene, or fluorine. Within the high symmetry group, we must next identify whether the point group have whether the molecule has an infinity center. If an infinity center is not present, then we will assign it to be in the TD point group, as in the case for methane. If an inversion center is present, so we'll move to the yes, it is present. We then need to determine whether a C5 rotation is also present in the molecule. If we do have C5 rotation, the point group of the molecule is IH. If we don't, such as fluorine, if the molecule does not contain C5 rotational axis, the point group of the molecule is assigned to be as OH. For example, hexachlorophene, if the molecule then does not have multiple C3 or rotational axis, so we're gonna go to this part, right? Then we must identify whether it even contains any rotational axis. If the molecule does not contain a rotational axis, so if it doesn't contain the rotational axis, we go right here. Then we're gonna ask the question, molecule which does not contain rotational axis can be the example. You can use tartaric acid or thionyl chloride or bromochlorofluoromethane. The molecules then will fall under the low symmetry groups. Then we have to determine whether that molecule that contains a mirror plane. So this is the sigma sign. Sigma n is the sign for the mirror plane. Sigma h, horizontal mirror plane. If a mirror plane exists, as in the case of thionyl chloride, we can assign the molecule to CS point group. If the mirror plane does not exist, but we identify that the molecule has inversion center, we would then identify that molecule as being part of the CI point group, such as in the case for mesotartaric acid. If the molecule does not contain an inversion center, so there is no inversion center, then it only has the identity symmetry element and is assigned to the C1 point group, such as in the case of bromochlorofluoromethane. Okay, so now we go back to this point. If the molecule does have a rotational axis, we need to next determine whether the molecule contain a second C2 rotational axis which is perpendicular to that first identified axis. If the molecule does contain an additional C2 rotational axis, which is perpendicular to the primary rotational axis, where the primary rotational axis has the highest end value, we know that we are looking at a molecule within the dihedral group. So we're gonna look at this part here. Dihedral group molecules example can be palatinate, staggered ferrocene, or biphenyl. If the molecule contain a mirror plane which is perpendicular to the primary rotational axis, it is assigned to the DNH point group, where the N is the value of primary rotational axis, such as in the case of tetrachloroplatanic molecule, which is in a D4H point group. If the molecule does not have a perpendicular mirror plane but does have the mirror plane which is parallel to the primary rotational axis, it is then assigned to the DND point group. For example, staggered ferrocene, that is classified as being in the D5D point group. Then, if the molecule does not if the molecule does not have any mirror plane, it is in the DN point group, such as biphenyl, which is which has the D2 point group, which fall under D2 point group. Molecule that only contain a single rotational axis fall under the monohedral point group, such as your hydrogen peroxide, sorry, water, tetraphenyl methane. These are all the example. Now, if the molecule has mirror plane perpendicular to the rotational axis, then it is a member of CNH point group, such as trans 1,2-dichloroethylene, which has C2H symmetry. Molecule that contains a mirror plane which is parallel to the rotational axis are classified as being in the CNV point group, such as your water, which has C2B symmetry. If a molecule does not contain any mirror plane but has an improper rotational axis, such as in the case of tetraphenyl methane, we assign the molecule into the S2N point group, or the N is the value of primary rotational axis. Any molecules that contain a proper rotational axis but lack mirror planes or improper rotational axis are then classified to the CN point group. For example, hydrogen peroxide, which has C2 symmetry. The correct identification of the symmetry of a molecule or an active site is very important in their characterization using spectroscopic techniques. We're going to be learning those in future.